Well, thank you very much, Lance, and thank you to everyone who's attending this session today. I'll be talking about a new technology that is just coming to the market right now, based on transceivers that are powered by 5 nanometer silicon DSPs that can deliver baud rates up to 140 gigabaud, and how this is truly going to revolutionize high performance optical networking in terms of achieving a set of wavelengths for optical transport that we have not been able to achieve before, and what this can mean to your network, and really how it's going to bring optical networking to the next level. As Lance said, we have Rafi Lehman, who's head of the Apollo PLM, that's our optical networking solution here. He is here to answer any sort of next level of questions that I sort of feel that's best addressed by him. And we want to make it conversational. So if you have questions during this discussion, please put them in, and we'll be trying to address them on the fly itself. So let's get started. So just a little bit of background, the role of optical networks. Really, optical networks, the way I see it, underlies our global information economy. And it's doing that by transporting huge volumes of information across long distances. And long distances could, we hear, in anywhere just across a city, across a region, across a country, across an ocean. And moreover, it's doing this at an extremely low cost per bit. The fact that we're having this webinar today is because we have an underlying infrastructure powered by fiber optic communications, which is allowing us to converse on a worldwide basis in this video format that we're so successfully doing today. And what we need to do as an industry, as the amount of information that we're transmitting continues to grow, and new technologies that are using this, such as AI, as an example, will call for even greater amounts of information. We have to find ways to continue lowering the cost per bit. And that's what I'll talk about as well today. So some of the questions that I hope to answer today with this session is, first of all, why is it important that we need wavelengths in multiples of 400G? 400G is not a magic number. It's a number which is derived from other things which are taking place in the industry. Another aspect that I'd like to bring to the forefront is, while we're talking about optical communications, it's still to a large extent being powered by silicon, specifically DSP technology. And I want to talk about how DSP technology has a role in delivering faster optical wavelengths. Finally, I'm going to be talking about this new technology that I alluded to at the beginning. It's all about 5 nanometer silicon technology that can deliver baud rates up to 140 gigabaud. And what this can do in terms of these multiples of 400G, we'll see that we can get 1.2T wavelengths for short haul, 800G wavelengths that can cover entire metro regional spaces, and 400G wavelengths that are virtually unlimited long haul. And then finally, a little bit of commercial stuff, and really that's right at the end of this discussion. Most of it is not commercial. But we are bringing this kind of solution to the market right now in a platform which we call OT, or Optical Transport 9408. It's a new 9400 series of platform that Ribbon is offering. And we'll show you how we can deliver these capabilities with unprecedented density and power efficiency. So just as a bit of a background, in case there's a few sort of newbies to optical networking on the call today, what are optical links all about? So optical links all are about wavelengths of light carrying information. What we see on the left is you can see video, you can see data, you can see storage, you can even legacy sort of TDM type of signals. But what happens is these are services that need to be carried from one location to another, increasingly going from a data center, say, to an enterprise, or between data centers themselves. And what we're doing with optical networking is we're mapping these services onto these wavelengths of light and then transmitting these wavelengths of light over an optical fiber to the destination. What makes optical networking so efficient is that we can put multiple wavelengths of light onto a single fiber that run parallel to each other without interfering with each other. And moreover, what we can do is we can amplify all these signals in unison, again, without having to bring them back to their original sort of electrical or services domain. In essence, this is what optical networking is all about: mapping services onto wavelengths, combining these wavelengths onto a single fiber and then transmitting them together. So what's driving optical networks from a requirements point of view? And really what it comes down to, as I said before, we're living in an information economy today. And at the heart of the information economy are data centers, where the applications reside, where the data resides. Everything to a very, very large extent is going to and from data centers and in between data centers themselves. So what takes place within data centers needs to express itself outside of data centers. And the main service for transmitting information within a data center is using high-speed gigabit Ethernet. Today, it's primarily 100 gigabit Ethernet. It's moving to 400 gigabit Ethernet. And we see on the horizon, as the next step beyond this, not shown over here, will be 800 gigabit Ethernet. So the major need in terms of what's driving optical networking is to transport these signals that originate within the data centers beyond the data center walls. I call it breaking down data center walls. And in fact, this is one of the pieces of collateral that you could also extract from this platform. I think if you go to the if you go to the paperclip icon on the right, you'll see a number of collaterals that you can take regarding the solution, regarding this whole direction. And that's one of the pieces called breaking down data center walls. So the major need is to transport this 100 gigabit and 400 gigabit Ethernet traffic. Now you see that the sort of DWDM lines are thicker for short haul, a little bit thinner or medium size for metro regional, and thinner for long haul. And the reason for that is pretty straightforward. There are limitations in terms of the speeds that you could achieve based on the distances you have to traverse. While fiber optics is extremely efficient, it's not infinitely efficient, of course. So you can transmit higher speeds for short haul, some in-between speeds for metro regional, and lower speeds for long haul. And what I'm going to show over here is the kind of goal that we expect to be able to see in the near term with this new technology that's coming to the market right now is 1.2 terabit per second wavelengths for short haul, say up to about 100 kilometers, 800G for metro regional, perhaps about to 1,000 kilometers, and then 400G for long haul, virtually unlimited. You can transport that today across the Pacific Ocean if you wanted to. So there's a very nice mapping in terms of what the needs are, in terms of the traffic requirements coming from the data centers, to how we can map this into wavelengths from a practical point of view for transporting these services over different lengths or different types of distances in a very practical way. And this just gives you some kind of sort of geographical representation of what this might look like. I just took maps of the United States, I took maps of Europe, and I sort of mapped on what you could achieve with 1.2T. And what you can see over here, I've tried to locate some of the major cities in each of these areas. Of course, if you're coming from other regions in the Far East, in India and South America, you can think about what this might mean within your own region as well. But you can see that you can do really 1.2T and cross entire cities, which is very important because often what you'll have is data centers that are replicating each other's data sitting at different points across the city for security purposes and survivability purposes. And now you have an ability to do high-speed transport among those data centers. You see 800G that you can do with the extended metro, or what I even call regional communication, up to about 1,000 kilometers, perhaps even a bit more than that. And again, you can see that for major metropolitan areas that I've mapped out over here in this maps. And then 400G is virtually unlimited. It can cover the entire geographical regions, the entire length and width of the United States, the entire length and width of Europe. So this is the kinds of practical deployments that can be achieved for transporting 100 gigabit Ethernet and 400 gigabit Ethernet transport. So the question now is, how do we get there? And what I was looking for with this session was to make it a little bit educational, a little bit semi-tutorial, and maybe sort of give people a bit better appreciation of how we're getting there with this technology. So what it really comes down to is optical transmission. And of course, the actual coherent optical transmitters and coherent optical receivers are infinitely more complicated than the diagrams that I'm showing you over here. This is just mapping out some of the key aspects of this. You'll see the bit stream coming in at the left. You'll see the other bit stream coming out at the right, running over the fiber optic link. The main point that I'm trying to show over here is that in coherent optical transmission today, both on the transmit side and the receiver side, there is both an optical component in terms of the lasers and the modulators, and there's an electrical component in terms of providing digital signal processing on the signals themselves in terms of how they're encoded, and then finally how they're decoded. So it's heavily dependent on digital signal processing technology to achieve the kinds of rates that we're able to achieve with fiber optic transmission today. And that's really the entire purpose of this particular slide. What's more important, though, is how do these aspects influence each other? So when you're looking at achieving particular line rates, and here I saw 400G, 800G, and 1200G, or 1.2T on the right. Of course, it could be any other rates as well. It really comes down to just a few different factors. One is modulation, and this is the number of bits that you can map onto a particular symbol, and I'll show that on the next slide. So you're probably familiar, of course, with different kinds of modulation like QPSK, and then different levels of encoding called QAM, quadrature amplitude modulation. And the higher you go in terms of the density of the modulation, the more number of bits you can carry. The next part in the equation is the baud rate. And I've left that blank for now because we'll get to that later. But that's how fast you can send those symbols across the fiber optic link. And then you also have to consider that there's two polarizations of light. So you get a doubling effect there. But then on the other hand, you also have to remove some of that transmission speed for overhead for forward error correction. And in the sort of examples that I'll give, I'll assume about a 20% reduction. It could really range between about 15% to about 30%. It really depends on various aspects of the solution, but 20% say sort of a good sort of a general guideline. And this will bring you to the line rate itself. So you might think to yourself, well, since I can use higher and higher modulations, why don't I just, go for higher modulations? And that's a way to get faster speeds. The issue here is that modulation density is inversely proportional to distance. You're running into the pure physics of the transmission medium. You're up against a hard wall in terms of how much you can further optimize modulation today. In fact, we're using today, all leading vendors of these kinds of solutions are using something called probabilistic constellation shaping. So again, while we talk about things like QPSK and 8 QAM and 16 QAM, etc., these are just really approximations, based on the standard way of talking about modulation. In fact, it's actually achieving slightly better using this PCS than what's being shown here today. But it's really at the limits of what can be done. And to show that diagrammatically, I've put this together. So again, this is showing the sort of the standard kinds of modulation. You see at the bottom QPSK, which is also called 4 QAM, and that just uses 4 symbols. And those 4 symbols can carry 2 bits. You go to 8 QAM, that uses 8 symbols. You can see those 8 different symbols in a constellation diagram, and so far all the way up the scale to 64 QAM. What these symbols are, of course, is a mixture of amplitude and phase. And you can think if you sort of put a set of axes through the middle of each of these constellation diagrams, and you drew a vector from the middle to any one of those particular points, it would represent an amplitude and a particular angle within the 360-degree circle. And that would be where that symbol would appear in terms of when it's being transmitted, and then when it's discovered, or when it needs to be recovered at the far end. So I think you can see intuitively that the denser the modulation, which relates to the higher amounts of information you can carry, just does not propagate as well without getting the symbols getting what I would call smeared into one another, which makes it impossible for them to be recovered at the far end, which is why you're running into the physics of modulation density being inversely proportional to distance. And today, while we're showing these as discrete modulations, in fact, what we have is an ability to do continuous types of modulation going even between sort of odd bits. So it's not going to be like 2 bits or 3 bits or 4 bits per symbol. It could be something like 4.5 bits or 5.2 bits per symbol using things such as probabilistic constellation shaping. But the message here is modulation density is inversely proportional to distance. So the question is, what do you do? And the answer is it really comes down to the DSP technology. So the DSP technology is how fast we can send these symbols, and that's the baud rate. So advances in silicon DSP technology is the main source of faster line rates in terms of how we can process these symbols. And what I'm showing here are the kind of advances that have been taking place in the industry the last few years. Going back about 4 years in 2019, we saw the introduction of 16 nanometer DSP technology, which is operating at 70 gigabaud. Just over 2 years ago in 2021, the industry introduced 7 nanometers, which was at 95 gigabaud. And now this year, we see the introduction of 5 nanometer technology, which is enabling baud rates all the way up to 140 gigabaud. So practically, what does this mean? So here's some example, and I'm just using 16 QAM as an example to sort of, give you a feel for what the different baud rates mean. So 16 QAM is 4 bits per symbol. Say we're running this with the old 16 nanometer technology, and still around today, running at 70 gigabaud. You have times 2 polarizations, and I'm talking about a 20% effect, so it's like 0.80. And that gives you a line rate of just over 400 G. If you ramp that up to the previous generation of technology, 7 nanometer, 95 gigabaud, what that does is enable you to just get over the 600 G level. And then finally, by using what's available today, just coming on the market now, using the 5 nanometer, 140 gigabaud technology, we're able to get well over 800 G. So you can see through these examples how the baud rate has a direct impact on the line rates that can be achieved. So here's a way to look at this schematically, if you like. And I've mapped this onto a graph showing short haul, metro regional, and long haul. So when we had the 16 nanometer, 70 gigabaud technology, essentially the fastest rates that we were able to achieve, and this was only for very short distances of about 100 kilometers, was 600 G. For 400 G was still a very good technology. You can go about 1,000 kilometers, and to go much longer for long haul, this was really limited to 200 G speeds. So until a few years ago, this was the best that we could do. When we had the advent a few years ago of 7 nanometer 95 gigabaud technology, you can see the jump that's been able to be achieved. So here for the short haul, we're able to get 800 G. And a number of companies were talking about 800 G for the last couple of years, but practically it did not go very far. I show here 100 kilometers. Maybe if you had some ideal fiber conditions, better amplification, you can go maybe a few hundred kilometers, but not much further than that. 1,000 kilometers would bring you down to 600 G, and then you had pretty respectable, say 300 G up to about 3,000 kilometers. And again, by the way, what I'm showing on this chart here are what I would call typical results. I'm not trying to show the results of hero experiments using best-in-class fiber, best-in-class Raman amplification, etc. Just the kinds of speeds and distances that you would see in typical commercial deployments in your networks today. So when we start applying what we can do with 5 nanometer technology, we now see the next level of jump. So what we're able to do is achieve 1.2 T wavelengths. Again, this would be using, the equivalent of 64 QAM, up to about 100 kilometers, very, very dense modulation. 800 G, which is really a nice spot for the performance of this technology, is very comfortable at 1,000 kilometers. So whether you're talking 1,000 kilometers, say, or about 650 miles, this covers fairly wide swaths of geography. So you have really, really good coverage with this. And then, as mentioned before, 400G, it shows 3,000 kilometers, but it can actually go quite a bit further than that, particularly with D-type submarine cable. We've already shown that it can go across the Pacific Ocean. And the other important point here is that by going to these higher speed wavelengths, what we're doing as an industry is we're continuing to lower the cost per bit. Because if you take a look, for instance, at any of these technologies, once the technology is mature, so I'm talking about, say, from the time it's introduced to maybe sort of a year or a year and a half after that, everything is coming sort of to an equivalent level of cost. So today, so a few years ago, I would need a 400G wavelength for 1,000 kilometers. That would be roughly the same cost a few years hence for a 600G wavelength for 1,000 kilometers using 7 nanometer 95 gigabaud, which would be roughly the same cost today, or maybe in, say, a year from now, once the technology starts to become much more mature, for a 5 nanometer 140 gigabaud. So by carrying more information on a single wavelength, which is the most expensive part of the solution, what we're able to do is continually lower the cost per bit. While we're talking, we have a question here, Rafi, so maybe this is time for you to come in. Why is it not possible to increase the baud rate without reducing CMOS size of the DSP?
Well, yeah, it's a nice question. So basically, it is a matter of processing. It's ability to process the signal. So in order to process the signal at the fastest speed, you need to go to lower, to lower geometries, and then this is, of course, there is also the optics that is involved that need to work at this rate. But usually what is really limiting is the ability of to build an ASIC that can process those signals at the fastest rate. And then if you need to go to 140 gigabaud, then you need the 5 nanometer process. In 7 nanometer process, you can do either optimize this what was done for performance, or you can optimize for power, and then you will go for lower power.
Thank you, Rafi. And like I say, thank you. It's a good question. It really comes down to how you optimize your silicon technologies and the geometries of the silicon in terms of sort of shorter distances and achieving faster rates. So this is a view of a 5 nanometer 140 gigabaud transceiver. This transceiver here, it's called the SIM8. It's being produced by a company called Acacia, which we're using here at Ribbon. And what it features very, very nicely is two main controls. One main control is continuous baud rate. So in this particular case, you can tune the baud rate from a low of 68 gigabaud to a high of 140 gigabaud. And you can also control the modulation continuously. So like I said before, talking about discrete modulations is sort of a thing of the past, but it's good to sort of represent what's there. But in fact, what the technology can achieve today using probabilistic constellation shaping is continuous modulation with a resolution of about 0.1 bits per symbol. When you combine these, depending on the fiber that's out there, the kind of amplification you have out there, the actual channel conditions that are out there, how much bandwidth is available, what you can do is you can maximize the line rate and achieve a maximum channel fill for the bandwidth that you selected to operate at. And these things sort of play together. If you have a higher bandwidth, say up to about 150 gigahertz, then you usually are able to maximize the line rate. If you have, say, a lesser bandwidth that's available, then that could impinge and perhaps reduce your line rate. But what the nice thing is by having these modulation controls, you can maximize the line rate for any distance and channel width. And we're really operating right at the edge of the theoretical Shannon limit over here. And what you see is that we're able to tune this up from 400G, 500G, 600G, etc. I've just highlighted the main wavelengths that I've been talking about. But in fact, with this technology, you can support any speed in increments of 100G from 400G to 1.2T, again, depending on your distance that you need to traverse and the type of fiber conditions that are out there. And this is being satisfied by this pluggable technology called the SIM8. What we're doing at Ribbon is we're commercializing this technology in a new platform. This platform we're calling the OT9408. And this is a platform that's optimized for high density design. So by high density design, some people call these kind of platforms compact modular platforms. It has a 600 millimeter depth. And it has front to back airflow, which is found to be the most efficient type of airflow. This is a kind of engineering that was pioneered and used in data centers with hot to cold aisles, but it leads to extremely efficient cooling, even if you have a high density of equipment within the rack itself. And what we see using this technology, will be among the first to market deploying this 5nm technology, which will deliver the 1.2T short haul, 800G metro, and 400G unlimited long haul. The solution you see, this has 8 slots. This particular version that I'm showing over here uses 4 double slot sleds. You see the sled in the middle on the right. And each one of these sleds can take 2 independent SIM8 pluggables. So by doing this, you have a true pay-as-you-grow kind of architecture that you can purchase the sleds, then you purchase the SIM8 modules as you need them. And you don't have to sort of over provision the kind of bandwidth that you would require even before you're ready for it. So it's a very, very flexible architecture that way. All the modules are field replaceable, the sleds, the controllers, the power supply, the fans. And a few other things to mention. It does support, of course, 100 gigabit Ethernet and 400 gigabit Ethernet. Also, the hardware is ready as the requirements come out to support 800 gigabit Ethernet clients as well. Worthwhile emphasizing is its exceptional efficiency and density. So it provides extremely low power of about 0.12 watts per gigabit per second. And on day one, the architecture with the solution that you see here, you can get 9.6 terabits of capacity in day one. And we have a design which will be coming out with next year that supports 19.2T, again, in this 2RU rack. There's another question that's come in since then. Rafi, if you want to address it.
Yes. So
let me read the question.
Yeah, so the question is the Max DMAX which are already installed, do they need to be replaced with FlexGrid WSS, which can vary the grid spacing, or fixed grid Max DMAX will be preferred? So, so again, we can do. Jonathan mentioned that you want to run 140 gigabaud again at certain rate. So if you need 140 gigabaud, then or if you want 140 gigabaud, you need to take a certain max DMAX. So if there is installed max DMAX, of course we can tune the bandwidth of the signal according to the max DMAX, but you will not get the maximal performance. So let's say you have 112.5 grid that you're already working because you have been working with 96 gigabaud technology. So we can tune to this one. We can reduce our rate to this one and basically work with any grid that you will choose, or which is really fits the typical network. But of course, the best performance and for maximal performance, it's better to go to the fixed. So both options are valid.
Okay, thank you, Rafi. And the last slide, and then we can keep on discussing if we like, is that this technology and solution we're talking about is available today. It's coming to the market, but we're not talking about something in the future. We're talking about something that we can demonstrate for you today in your network, if that makes sense to do so. We can do this in a very short notice. And if you're interested, probably the best sweet spot for this technology is 800G. And you might want to see how far it can go in your network. 1,000 kilometers, 1,200 kilometers. Are there real limitations because you're working with some very old fibers, so maybe a bit less? But what this will allow you to do is really understand the way that this 5 nanometer 140 gigabaud technology with continuous modulation and continuous baud rate can provide the best solution in your network. We can run this as an end-to-end type of proof of concept, or we can run this using a loopback, depending on your conditions. And we're not really concerned in terms of the ROADMs that are in between. Sort of based on the question before, we can tune to the kind of technology that's out there. So, of course, in most cases, you'd likely be running some other vendors' ROADMs or some other vendors' optical line system. And we feel very comfortable running our wavelengths over this existing line system. And we show here an example of an 800G demo setup. So in summary, I hope we've answered some of the questions that I started out with today, which is why it's optimal to go to wavelengths in multiples of 400G, how DSP technology is sort of driving the ability to get faster wavelengths as we're now entering the 5 nanometer 140 gigabaud era, and hopefully let you know that Ribbon with our OT9408 is leading the industry in terms of bringing this solution to the market based on the SIM8 pluggable. And if you're interested in this or just even curious about it to sort of see the benefits it can bring to your network, please contact us. There's the way to do that is, again, if you go to the resources link, one of the links will bring you to a web page, which you can just fill out a very simple form, and then someone will contact you, and we can start discussing the details of how this takes place. If any of you have any other questions and you'd like to contact us directly, you can send me an email. It's jonathan.homa@ribbon.com. And I'd be glad to answer your questions directly. Again, another question that's come in. Hi, please explain again about MUX, DMUX, ROADM for this solution to work. So obviously this is a concern that's come in a few times. Rafi, do you want to maybe take
actually, yeah. So the ROADMs that again, MUX, DMUX, and the ROADM grid should be aligned. Okay? You cannot work with, let's say, without MUX, DMUX, and ROADM which is not flexible. So assuming that you are setting the spacing of the signal, let's say you are taking an existing MUX. Maybe let's take another example. I have a MUX of 100G spacing. And then I am setting my ROADM, which is it also can be either 100 or it should be like off flex grid or 100. And then you can run your lambdas, which are with the bandwidth, which will accumulate exactly those 100 gigahertz spacing. And for this, we have special modes where we are playing with the modulation, and we are playing and adjusting the width of the signal to a certain constraint, which is in this case is maximum. So, yeah, hope it was clear.
Again, if you're looking for more information, just please contact us, and we can have a discussion with you one-on-one on these things. So I thank you all. As I promised, I wasn't going to sort of make this an extremely long session today. I hoped I touched on some key points. Rafi was able to answer your questions, and we were able to sort of raise the visibility a bit about the real capabilities of this 5 nanometer 140 gigabaud technology for what I call revolutionizing optical networking. So, Lance, I think with that we could end.
Yeah, thanks, Jonathan, and thanks, Rafi, and thanks everybody on the call for your questions coming in. I just did want to point out again at the bottom, I believe left, there's a tab for attachments. Breaking down data center walls brief is there that Jonathan mentioned. The Apollo OT9408 data sheet is there, as well as a link that'll take you to that test drive option where you can fill out that simple form and get in contact with us so we can show you the technology up close and personal. So please check that out. You'll be getting an email from us later with some slides and a link to the replay, so be on the lookout for that. And as always, check out the Ribbon channel on Bright Talk for additional content, much of the same you saw here today, plus other great things from Ribbon and the telecom industry. But thanks again for joining us today. Really appreciate your time. Have a great rest of your week.